So in the previous lecture, we have discussed about the Chebyshev equation and Chebyshev polynomials. And what are the property of Chebyshev polynomial we have discussed in the previous lecture. Now the next section of this ordinary differential equation chapter is the some special study about the some special functions. So here we are talking about few special functions, in particular Legendre special functions, Bessel special function. We'll talk about that into this lecture. So here I can say about some thing which will be a solution of the Legendre equation. It is known as a Legendre polynomial. Okay, so we'll talk a solution of Legendre's equation. What is a Legendre equation? Is 1 minus x square y double s minus 2xy dash plus p into p plus 1 y equal to 0, where p is greater than or equal to 0. So p is a positive number, and this is known as the Legendre equation. So here we'll like to obtain a solution of this Legendre polynomial or Legendre equation at its ordinary point x is equal to 0. So the question is obtain the general solution of Legendre's equation at the ordinary point x is equal to 0. What is a Legendre equation is this which we have written. So if I call it this equation 1, then equation 1 can be written as it into its standard form, that is y double dash minus 2x upon 1 minus x square y dash plus p into p plus 1 by 1 minus x square y equal to 0. If I compare this equation with comparing above equation with y double dash plus p of x y dash plus q of x y equal to 0, we get p of x is equal to 2x minus 2x upon 1 minus x square. That you can see, this is your p of x and this will be your q of x. So the q of x is p into p plus 1 by 1 minus x square. Clearly this p of x and q of x are analytic at the point x is equal to 0. Hence we can say that x is equal to 0 is the ordinary point. So clearly p of x and q of x are analytic at x is equal to 0. Therefore x is equal to 0 is the ordinary point of equation 1. So if it is an ordinary point, we can talk about its series solution, and the series solution can be represented as let y equal to summation n running from 0 to infinity a n x raised to n is the solution of equation 1 valid for mode x less than r with some r greater than 0. So we have to substitute this value of y into the equation 1. So for that I need to know what is the y derivative of y and double derivative of y. So y dash will be summation n running from 1 to infinity n into a n x raised to n minus 1, and y double dash will be n running from 2 to infinity n into n minus 1 a n x raised to n minus 2. Substituting this value of y, y dash and y double dash into the equation 1, let us see what we get. What will be the equation? That is 1 minus x square y double dash minus 2xy dash plus p into p plus 1y. This is the Legendre equation is there. So therefore it is 1 minus x square y double dash, that is summation n running from 2 to infinity n into n minus 1 a n x raised to n minus 2 minus 2x into n running from 1 to infinity n into a n x raised to n minus 1 plus p into p plus 1 summation n running from 0 to infinity a n x raised to n equal to 0. If I separate this all the summation or and I'm multiplying this bracket with the things, we got summation n running from 2 to infinity n into n minus 1 a n x raised to n minus 2 minus summation n running from 2 to infinity n into n minus 1 a n x raised to n, because this x square is multiplied to this summation. Then this 2x is multiplied inside to this summation, then this will be minus 2x plus summation n running from 1 to infinity. Now 2x is multiplied inside, so it is 2 into n a n x raised to n plus p into p plus 1 summation n running from 0 to infinity a n x raised to n equal to 0. So what we have to do next? We have to convert this index with the same index. That is our objective. Or I can just change this x raised to n minus 2 with the same x raised to n. That is the way we can do first. So we'll do this index, or I can change this n minus 2 as power of n. So I'm replacing n minus 2 with n into the first summation. Here it is already x raised to n is there. Here is also x raised to n is there. Here is also x raised to n is there. So we'll change this n minus 2 to n into the first summation. Hence we got n running from 0 to infinity, because if I replace n minus 2 to n, then n is starting with 2. Now it will be n. So it will start with 0. N plus, instead of n, so n will replace with n plus 2. Instead of n, we will have n plus 2 into n minus 1. So it is n minus 1 plus 1 plus 2. So it will be n plus 1 a n plus 2 x raised to n. And the other thing, other summation will be stay as it is. So that we can write down as it is. Summation n running from 2 to infinity n into n minus 1 a n x raised to n minus summation n running from 1 to infinity 2 into n a n x raised to n plus p into p plus 1 summation n running from 0 to infinity a n x raised to n equal to 0. Now we'll write down this index will be similar. So there are terms with n equal to 0, n equal to 1, we have to write down separately. So when n equal to 0, we'll have 2 into a 2 x power 0. And here there will be term of x power 0, that is a constant term, plus p into p plus 1 a 0. This is the constant term we'll have. Plus when you have n equal to 1, substitute here. This will be gives you 3 into 1 plus 1, that will be 2, so it is 6a3. The x is there. There is only terms of x is here also. Then this will be minus 2a1 plus p into p plus 1, a1 into x. And then plus summation n running from all the things will start with 2 now. And we can write down that is as n plus 2 into n plus 1 an plus 2 minus n into n minus 1 an minus 2 n into an plus p into p plus 1 an whole into x raised to n equal to 0. Comparing the coefficient of powers of x, we get, so we will write down comparing coefficients both sides, we get this is equal to 0, this will equal to 0, and this quantity will equal to 0. So that will gives you 2 into a2 plus p into p plus 1 a0 equal to 0. 6 into a3 plus this both quantity contains a1, so that we can write down as p into p plus 1 minus 2a1 equal to 0. Next we have this quantity, that is, and all the other this quantity I am taking on the other side, so that will gives you n plus 2 into n plus 1 an plus 2 equal to, you can see that it is n into n plus 1 plus 2n, we can have that is this term, and minus, due to this quantity goes on the other side, this will become minus, so it is minus p into p plus 1 whole this quantity into an. So finally we'll have an plus 2 will be n into n minus 1 plus 2n minus p into p plus 1 upon n plus 1 into n plus 2 into an. From this we will have the value of a2, which we can write down minus of p into p plus 1 upon 2a0. This will gives you value of a3, which we can write down by taking this minus, so it will be 2 minus p into p plus 1 upon 6a1, and from this we can also have the value of a4 and so on. So this a3 I may rewrite, so here a3 will be this 2 minus p plus 1 by 6 a1, that can be rewrite as 2 minus p square minus p upon 6 a1, but 6 I can write down as a 3 factorial, and this I can write down p square plus p minus of p square plus p minus 2 upon 3 factorial a1, and this quantity can be factorized as p minus 1 p plus 2 upon 3 factorial a1. So this is the value of a3, this will be the value of a2. This 2n plus 1 also can be simplified. Let us simplify this, an plus 2. So now an plus 2 equal to, what we have it is n into n minus 1. So it is n square minus n plus 2n minus p square minus p. In the denominator we have n plus 2 into n plus 1 into an. So this can be simplified as n square plus n minus p square minus p upon n plus 2 into n plus 1 into an. This we can write as n square minus p square plus n minus p upon n plus 2 into n plus 1 into an. Now this can be factorized, n square minus p square can factorize as n minus p into n plus p plus n minus p upon n plus 2 into n plus 1 an. So this n minus p, you can say it is a common out from this. So this will be n plus p plus 1 upon n plus 2 into n plus 1 into an. So finally, what is your a n plus 2 we'll have here? It is minus of p minus n plus p plus 1 upon n plus 1 n plus 2 an. This is the recurrence relation with an we have, where n is start with 2, 3, 4 up to so on. So when n is 2, we'll have a4. So n equal to 2, we'll have a4, which is minus p minus 2 p plus 3 upon 3 into 4 into a2. The value of a2 is minus of p plus 1 upon 2 a0. If I substitute that value here, then we will have it is p into p minus 2 p plus 1 p plus 3 upon 2 into 3 into 4, so it is 4 factorial a0. For n equal to 3, we will have a5, which will be minus p minus 3 p plus 4. That means n equal to 3, you have to substitute here. P minus 3 p 3 plus 1, that it will be 4 upon 4 into 5 a3. Now the value of a3 we have calculated here, which we have this, which will be minus. Here is also we have a minus, so that minus minus become plus. We have p minus 1 p minus 3, and other one is p plus 2, so that is p plus 2 into p plus 4 upon, it was 3 factorial, so it is 3 into 4 into 5, so this is 5 factorial into a1. Same way you can have the value of n equal to 6 when I substitute n equal to 4 here. This will give you minus of p minus 4 p plus 5 upon 5 into 6 a4. But the value of a4 is this. So this will give you minus p into p minus 2 p minus 4 p plus 1 p plus 3 p plus 5 upon 6 factorial into a0, and so on. You can have further values, and you can substitute all these values into the power series. So hence the solution is y equal to summation n running from 0 to infinity a n x raised to n will be a0 plus a1x plus a2x square up to so on. So this can be separate into this form, that means you can see that when n is even number, then it will have a coefficient is a0. When we'll have odd number index, then we'll have a coefficient is a1. So this we can separate out with a0 plus a2 x square plus a4 x raised to 4 up to so on plus a1x plus a3 x square, sorry, cube, a5 x raised to 5 up to so on. And we'll substitute these values of a0, a1, a4 here. Then this will gives you a0 will be common out from each of them. a2, the value of a2 is minus of p into p plus 1 by 2 into x square. That is the value of a2 will have. The value of a4 we can have from this, that is this whole value, which is a positive sign. P into p minus 2, p plus 1, p plus 3 upon 4 factorial, x raised to 4. Then the next term is x raised to 6, or a coefficient of x raised to 6, which is this, which I am not writing. So I am just saying that it is minus of minus. So it is the term having the alternating sign here. Okay, plus a1. The value of a1 is common out, which I can take common, and the coefficient is 1 here, plus a3. The value of a3 is actually of negative sign. The value of a3 is minus of p minus 1, p plus 2 upon 3 factorial, cubed plus p5. Value of p5 is this whole value, which is of positive sign. So it is p minus 1, p minus 3, p plus 2, p plus 4 upon 5 factorial into x raised to 5, then minus sign up to so on, which is the general solution of the Legendre equation that I should write, which is the required general solution of Legendre equation. Now, if this solution is there, and if this value of p is an natural number or 0, so I may write down some remarks here which are very important, and due to this remarks actually you will get Legendre polynomials. If p equal to n, which is belongs to a natural number or 0, then the above solution becomes, what will be the above solution? Instead of n, so instead of p you will have n here. So what you will get is y equal to a0 into 1 minus n into n plus 1 by 2 factorial x square plus n into n minus 2 into n plus 1 n plus 3 upon 4 factorial x raised to 4 plus so on, plus a1 into x minus n minus 1 n plus 2 upon 3 factorial x cubed plus n minus 1, n minus 3, n plus 2, n plus 4 upon 5 factorial, x raised to 5 and so on. And this solution I may write down as y equal to a0 into y1 plus a2 into y2. What will happen if this n is an even integer? If n is an even integer, then which quantity from this y1 and y2 will be 0? Then you can see that the pattern is n into n minus 2, the next one is n into n minus 2 into n minus 4. So if n will be of the form 2m, then after the term, some term, this a1 will become polynomials. So this y1 will become polynomial, and if n is of the form 2m plus 1, that means it is an odd number, then this has the pattern n minus 1, n minus 2, the next term will be n minus 5 and so on. So after the term this n minus 2m plus 1, all the rest of the terms will be 0. So in that case, the y1 will be a polynomial. So what is conclusion? We can make out that is if n is an even integer, then y1 becomes a polynomial, and if n is an odd integer, then y2 becomes a polynomial. Okay, so this is the quantity we got. That means in any of the case, if n is an integer, then one of them, either y1 or y2, will become 0. So this polynomials also one may observe that if the y1 is 0, then it will contains only even powers. If y2 is 0, it always only contains the odd power. So any one of them, any one of the polynomial, if it is become a polynomial, then it will only contains even powers or it will contains an odd powers of x. That is also we can write as a note. Also note that this polynomials either includes only even powers of x or only odd powers of x. So there will be either will be even powers of x or it will have odd powers of x. Okay. Let's have the fourth node. Let n be equal to n and n equal to k. P equal to n and n equal to k. Then the recurrence relation I may call it that recurrence relation as some number. So this is the recurrence relation. I'm just calling this as number 3. So that recurrence relation 3 can be written as a k plus 2 equal to minus of n minus k, n plus k plus 1 upon k plus 1, k plus 2, ak, where k is running from 0, 1 to up to so on. Now, if you replace this is replacing k by k minus 2, we get kk will be minus of n minus k plus 2, n plus k minus 1 by k into k minus 1. See what I did it, I just replaced by k minus 2 here. So this is, instead of k we have k minus 2, so this is k plus 2, and here it is k minus 2, so it is k minus 1. In the denominator we have k minus 2 plus 1, so it is k minus 1, and k minus 2 plus 2, so it will become k into ak. Instead of k we have to replace k minus 2, so this is ak minus 2. So this we have to remember. Later on we will use this. Okay, so this we can note of this one, and we will use this to get another thing.